All right, let's just jump right in. We are talking about one of the absolute biggest puzzles in all of science. How in the world do you prove a theory is right when you can't, actually test it? This is the massive challenge facing some of the most mind-bending ideas out there today.
And yet, that's really the heart of it, isn't it? When you've got a theory that claims to explain, well, everything, from the smallest little quiver of energy to the entire cosmic web, where do you possibly start to see if it holds water?
So, here's the deal with string theory. Its promise is just incredible. The idea is to bring all the fundamental forces of nature together into one beautiful, tidy package. I mean, it's basically the ultimate goal in physics. But, and this is a huge but, the tiny vibrating strings it's based on are so small and require so much energy to see that we are nowhere near being able to detect them directly.
This right here, this is the question that probably keeps physicists tossing and turning at night. It's a real challenge to the whole scientific method. I mean, if you can't verify your ideas with real-world observations, are you still in the realm of science? Or have you drifted off into pure philosophy? It's a serious question.
So, you gotta wonder, right? Without the usual safety net of experiments, how do scientists make sure they aren't just getting lost in these incredibly beautiful mathematical worlds that, well, have nothing to do with reality? They need a different way to check their work.
And it turns out they've got one. Not a physical map, of course, but a kind of intellectual guide. A set of signposts that helps them figure out if they're heading in the right direction or if they've taken a wrong turn into a dead end.
And for our little journey today, our map is coming from a place you might not expect. Chapter 21 of the book, String Theory for Dummies. Yeah, seriously. It actually lays out a super clear, really structured way to think about this massive problem.
And this is the secret sauce right here. The book makes a really important distinction. We're not talking about 10 experiments, because remember, those are pretty much impossible for now. We're talking about 10 tests. It's a totally different thing. It's a way of judging the theory on its own merits, its logic, its consistency, its sheer explanatory power.
10. That's the magic number. The book gives us 10 concrete benchmarks that a theory like string theory has to hit just to be considered a serious contender. Think of it less like a quiz and more like a gauntlet, a series of rigorous trials for a revolutionary idea. So let's see what they are.
Okay, let's be super clear on what a theoretical test is. This isn't about firing up a giant atom smasher. Nope. This is about looking inside the theory itself. Is the math solid? Are there any glaring contradictions that make it fall apart? And maybe most importantly, can it explain the universe we can already see?
You've probably seen these For Dummies books, right? This whole checklist approach is kind of their signature move. It's brilliant, really. They take something that feels impossibly complex and just break it down into a simple, structured list. It's how we can even begin to get a handle on the untestable.
So what are we talking about here? What kind of hoops does a theory of everything actually have to jump through to get taken seriously?
Well, the 10 tests in the book boil down to a few core principles, and the absolute biggest one is this. The theory has to explain everything we already know is true. It can't just be some cool new idea floating out there. It has to successfully rebuild, from the ground up, the two pillars of modern physics, the Standard Model for particles and Einstein's general relativity for gravity. If it can't do that, it's dead in the water.
Exactly. That's the foundation. Another huge test is that the math has to work, with no weird paradoxes or holes. And then there's the really exciting one. It has to make new, bold predictions. Even if we can't test those predictions today, the theory has to tell us something new about how the universe works, something we didn't know before.
For example, one of the 10 tests is a big one. The theory must include gravity. Our source material is crystal clear on this. Any supposed theory of everything that can't reproduce what Einstein figured out about gravity, it's a non-starter. But the tests go deeper, asking if the theory can solve other huge mysteries like, hey, what is dark matter? Or what really happens at the center of a black hole?
So you see, this whole framework, from explaining old science to solving new puzzles, is so much more than just some academic exercise. It's a quality control system for our ideas about reality itself. It's what keeps physicists honest while they're exploring the furthest frontiers of knowledge. And in the end, that's what this is all about. These are the rules of the game. They provide the discipline, the structure that separates a powerful scientific theory from just wild speculation. It's the playbook that allows science to keep pushing forward, even into the unknown. Thinking about all this kind of blows the whole thing wide open, doesn't it? It makes you ask a much bigger question that applies to any new idea, really. When we're staring into the darkness, exploring places we can't see or measure yet, how do we decide which paths are worth following?
So, I'm going to leave you with this to chew on. If you had to add an 11th test to that list, just one single, ultimate hurdle that any new theory about our universe absolutely, positively had to clear, what would it be? For you, what's the most important test of all?